Okay, I can start, right?
Yeah, so
Yes, you're live.
yeah.
Okay, so hello everyone. I'm Salma, and thank you for inviting me to present. Okay, thank you for inviting me for this presentation to present our research group. And I'm going to talk about the integration of Hyperledger Fabric and ROS2 for distributed robotic systems and some results of our real-world experiments in our lab. So for my presentation, I will start with a small introduction about our research team, TIERS, in University of Turku. Then I will give an introduction of Hyperledger Fabric and ROS2, and then go over some real-world examples and scenarios, and then finally talk about the results that we had. Turku stands for Turku Intelligence Embedded and Robotic Systems, and our research verticals consist of edge intelligence, resilient autonomy, distributed systems like swarm intelligence and collaborative autonomy, and so on. And in this presentation, we will explore how the blockchain technology can be integrated with advanced robotics to enable trustable data sharing and robot control. And we will examine real-world examples and scenarios of scalable, collaborative, and reliable robotic systems, and discover their potential in various industries. I know you know, but I'm going to give some introduction about the fabric also. As you know, Hyperledger is one of the biggest platforms in the permission blockchains, and it is an open source project based on Linux Foundation. It provides projects and frameworks to businesses and developers to build the blockchain networks and applications. And it aims to ease the collaboration between developers, enterprises, and businesses in the field of distributed ledger technology. And as the advantages, it offers a robust set of features that makes it suitable for integrating blockchain into distributed robotic systems. Its permission network architecture ensures that only authorized participants can join the network and access shared data. And the modular architecture allows for flexibility and customization, enabling developers to tailor the blockchain network to their specific requirements. And it supports smart contracts, enabling the execution of automated businesses logic on the blockchain. But if I want to talk about the robotic side, I'm going to talk about the ROS, which is basically, it's going to be the main talk today. And what is ROS? Before the introduction of ROS, robotics development was often lacked a standardized framework. Developers had to build their own custom solutions for communication, coordination, and integration of robots components, leading lots of efforts and collaboration among researchers and sharing the codes and resources were challenging. The absence of a unified platform made it harder to prototype, test, and deploy robot applications, increasing development's time and complexity. ROS revolutionized robotics by providing a common framework, fostering collaboration, promoting modularity, and simplifying the development process, accelerating the advancement in the field. First, ROS developed. ROS is also known as ROS1. It was initially released in 2007 and has since become widely adopted in the robotics community. It provides flexible and modular framework for developing robot software. It allows developers to break down complex robot applications into smaller, reusable components called packages, promoting code modularity and reusability. It uses publish and subscribe messages system, which we call them topic, to enable communication between different components of the robotic systems. And It primarily supports single host systems and is mainly used for research and prototyping applications. It has a large ecosystem of packages and tools developed by the community, making it easier to leverage existing functionality and collaborate with others. If you see, I put an example of how ROS1 works and how robots can communicate with each other. In the presence of ROS master, we can have publisher node and subscriber node where the data can be transferred through the ROS topic so that multiple robots can easily communicate with each other and transfer the message between each other. Here you can see the ROS communication where, for example, it is an example. Camera can be as a node which publishes its data on a topic. We can also have a node for processing the camera data and one node for example, recording the data. And the processing node can subscribe to the camera topic and publish its processing results on another topic. And on the other hand, the recording node can subscribe to these topics and record all the data received from the camera node and processing node. But ROS1 has also limitations. It doesn't provide native support for real-time systems or safety-critical applications. Package developed for one specific ROS distribution may not always be fully compatible or work seamlessly with other ROS distributions. So sometimes we need to change the whole codes and whole codes for other distributions. It was primarily written in Python 2, which has become an outdated version of the language, and also it was designed for research and development purposes rather than for deployment in security-sensitive environments. It lacks of native support for external networking and distributed system. It was designed for single host systems, and communication between ROS nodes was primarily intended for local machine communication. With the presence of these limitations, ROS2 emerged. ROS2 is a modern framework for building robot applications. It improves Open ROS1 with enhanced performance, scalability, and support for real-time and safety-critical systems. ROS2 promotes code reusability, collaboration, and interoperability, making it easier to develop advanced robot applications. With the distributed architecture of ROS2, it enables communication across multiple machines, and its modular structure separates components into nodes for improved flexibility. And message-based communication in ROS2 uses a publish-subscribe model for data exchange. With this architecture, ROS2 provides a powerful platform for building advanced robot applications. Here, if you can see, basically topics in ROS2 are transferred in this way, where we can have multiple publisher and subscriber nodes. The biggest change that came with ROS2 was the selection of the DDS middleware for the communication layer, which has strengthens the communication between robot components with its decentralized public subscribe architecture, and we don't need any ROS master in ROS2. ROS includes mature open source libraries to be used for navigation, control, motion planning, vision, and simulation purposes. The 3D visualization tool like ROS, named ROS, and the simulation tool Gazebo are seen as useful tools for robot developers. And also apart from this, OpenCV library is a library used for detection purposes in ROS2, which we have also used in our scenarios. Now let's move to some of the real-world examples and some scenarios that we had regarding integrating ROS2 and Fabric. Over the past 2 years, we've been working on integrating Fabric with ROS2 using both Go language, Golang, and more recently with Node.js. For ROS2, both Go and Node.js client libraries are community-backed, as the main supported languages are Python and C++. So if I want to talk about our first scenario, real-world example, a Hyperledger Fabric DLT network is interfaced with ROS2 for managing autonomous robotic fleets. In this scenario, we introduced the framework for integrating ROS2 with a Hyperledger Fabric for distributed robotic systems, and also analyzed the impact of integrating Fabric in robotic systems with a performance and a scalability study, and experimental proof of the proposed framework for an inventory management application with ground and aerial robots. Here, this diagram shows the framework architecture and key components. The Fabric network is hosted in a cloud with a Go-based web interface for visualizing the ROS2 data stored in the different channels, and a command interface for inputting user instructions. Fabric is hosted by a set of organizations, contain peers, certificate authorities to verify their membership in the network. Existing of the private data channel is one of the key components differentiating Fabric from other blockchain solutions here. In this framework, robots are members of the Fabric network and also shared ROS2 network. You can also see the important applications of smart contracts for industrial robots, like Ledger can be used to record sensor data, ROS2 data type, or so on, and web application can be used for visualizing data and sending comments to the robots, and so on. If I want to give an algorithm example of an application for such purpose, you can see this algorithm. Another benefit of DLT, in addition to the mutable and auditable records, as you know, in the built-in security features and identity management, which can be exploited, for instance, in interfaces for users for control either individual robots or fleets. Any collaborative decision-making process can be implemented through smart contracts, which we are basically using to ensure that all robots obtain the same result. This is applicable to role allocation or resource distributed problems. For the experimental part of our scenario, you can see the implementation diagram of the different software modules running in different nodes here. We have used the ground robots, EAI Dashco platform, and the UAV X500 quadrotor frame embedded with Pixhawk 5X flight controller running with the PX4 firmware. For this experiment, we used 6 OptiTrack cameras for navigation of the robots in our arena. Robots were running ROS Noetic under Ubuntu 18, but the localization and object detection were all running in ROS2 proxy, and we have used ROS1 bridge to forward data from Noetic to Foxy from ROS1 to ROS2. Fabric applications were running onboard the robots, but connect to the peers running on the separate computer in the network with the same Intel Core i7 processor. And for the object detections, we used YOLOX, and Fabric has been brought up for secure data management and robot control. We used 2 smart contracts, one for storing the path tracking and one for storing the location of the detected objects in the asset. And for each robot, one application with different functions for controlling the assets has been used. And we have used a series of shelves set up in the room of 40 square meter containing different objects from the COCO dataset categories. And for this scenario, we have checked and analyzed the CPU and memory usage during the experiments, and to see if using and integrating Fabric in our system would affect the system or not. And we have also checked the YOLOX usage, and the CPU usage is in blue and memory is in pink. So as you can see, having Fabric for secure data sharing is negligible. And so the proposed framework can be adopted in a wide variety of robotics platforms. And we have also measured the latency of the data storing in the blockchain when the application nodes is running in the robots connected to the computers running in the order and the peers nodes via Wi-Fi. And here you can see the distribution of the latency of the main 4 settings, where data from 15 seconds is accumulated and over 200 hertz of ROS2 data being pushed into the smart contracts. We were trying to try this with different batch timeout and maximum message to see the difference latencies also. As a second scenario, you can see here the blockchain is used for high-level mission commands, predefined robot paths, for triggering multi-robot cooperative actions based on chain-recorded robot states like docking and landing the drone, and switching operation modes for active and deactivating the ultra-wideband beacons. Detected objects are also stored in the blockchain. With the ultra-wideband, I need to give an introduction about that also. What is it? Ultra-wideband technology merged as a robust solution for localization in robotic systems, especially for GNSS-denied environments. It can provide centimeter levels of accuracy at low cost. It also has the advantage that it doesn't depend on environmental conditions such as light or there is any dust, like what would happen with the cameras and lidars. It is also more accurate than Wi-Fi or Bluetooth and less prone to interferences. Here you can see ultra-wideband is a radio frequency technology that is used for indoor localization, since these devices are more affordable than other indoor localization solutions like OptiTrack cameras that we used for our previous scenario, is attracting increasing attention. Anchors and tags are two types of nodes used in ultra-wideband localization to obtain the positions of the tags. In most anchor-based scenarios, the locations of the anchors must be known. So if we the coordinations of the fixed anchors nodes are assumed to be known by the system for our calculation, and if we have enough fixed nodes and also the location of that, coordination of them, depending on the ranging method implemented, the tags can be estimated their distance from each anchor and calculate their own location using different algorithms like TOF, time of flights, which in our case is that. So for this scenario, we plan the path for our telodrome and dashgo to inspect warehouse-like environments and store the information they get about the objects, store them in the blockchain. We utilize the Fabric smart contract for logging historical data and collaborative decision-making for drone landing, and we also utilize ultra-wideband localization for following predefined trajectory, while the docking smart contract triggers the activation of the anchors in the ground robot for more accurate relative localization while docking. The experimental platform of this scenario consists of the commercially Telo MAV and ground robot. As you can see, the drone is equipped with the ultra-wideband module for localization. We also utilize the drone camera for object detections, with the camera feed being available through a WebSocket connected to a controller computer. The ground robot, EAI Dashgo, is equipped with the sensors and camera, and also RealSense T265 RealSense camera for the ego motion estimation. For this experiment, we have 4 ultra-wideband nodes, modules with custom firmware. They have been deployed for robot localization, and also we have 5 extra ultra-wideband nodes which has been used on the Dashgo platform for more accurate docking of the Telo. For these experiments, like the previous one, we have the objects from the COCO dataset categories, and the arena is 40 square meter room. So on the software side, the Dashgo robot runs ROS Melodic under Ubuntu 20, and the main driver, localization and object detections are all running in ROS2. The Fabric application running onboard the robots are connected to the peers running on a separate computer and network. To forward the data, we have used Bridge like the previous one, and to obtain the camera image of the Dashgo at a frequency of 30 Hertz. Even though they are forwarded to the object detectors at 5 Hertz, the USB CAM package has been used, which is available in both Melodic and Foxy. To implement the different parts of the system, we have used Go programming language, Golang, whenever possible, has been used to increase the potential for integration between the different parts of the system. We have 5 smart contracts implemented in the system, 2 for storing each robot's past history, and 2 for storing the locations of detected objects by each robot, and 1 for updating the battery level of the telo and also landing decision-making for both robots. 1 application containing different functions such as creating assets and read and updating and changing the assets has been used for each robot also. This figure shows the trajectories of the robots during the experiments, and towards the mission ends, as it can be seen, after more than 3 minutes, the positions converge when the telo drone lands on the dashboard. And the bottom figures show the distribution in the time of the object detection detected by the telo and dashboard. And we have also analyzed the memory and CPU usage by Fabric and YOLOX, and we got the same result, which usage of Fabric is negligible. And we have also analyzed the latency, this figure shows the latency distribution of 5 smart contracts, where we had over 200 Hertz of ROS2 data stored in the average. And if I want to show it so it be more visualized for you, so the idea is that both telo and dashboard start to explore the place, and whenever they're exploring, whenever the battery level of the telo goes beyond the threshold, then the docking command is sent to dashboard and telo, so they both go to the landing position, and while they both arrive to that position, the anchors on the dashboard activates. So the telo use those ultra-wideband anchors on the dashboard to land, so we have more accurate landing. So this is another scenario with the same idea, but using the Fabric smart contracts as running the role allocation to determine the corresponding roles for each node shown here. We have 4 ultra-wideband localization of the system. We use both time of flights and TDOA to minimize the disadvantages. And the Hyperledger Fabric aims to secure data management and robot control. The implementation has 2 smart contracts, 1 contract to store the past history of 6 mobile ultra-wideband nodes, and the second one that implements the role allocation algorithm and saves the roles in the network. So the core idea for the role allocation is to keep the passive nodes toward the centroid of the system inside the convex envelope, and the active nodes towards the outside. So the idea is that I don't want to go inside this, but using the smart contract for role allocation was basically for this idea. And for the hardware, we utilized the 6 Jetsons with Jetson Nano modules, and we have ultra-wideband Decawave developed modules with custom firmware to enable time of flight and TDOA and transmission scheduling. And the backbone wireless network is also implemented. And we have also used 6 OptiTrack cameras for motion capture system were used, and 1 global controller with Core i7 processor for robot coordination and to run the localization algorithm. On the software side, the Jetsons are running ROS Melodic in Ubuntu 18, 1 computer to serve as a coordinator and run localization. Also, a ROS1 to ROS2 bridge is implemented before. And ROS1 for Jetson and ROS2 for the Hyperledger Fabric application. And the role allocation algorithm is implemented in 3 different ways. One way was in ROS1 Python node, one way was in ROS2 with RCL Go, Golang, and another way was in Fabric smart contract in Golang, with the aim of comparing the performances later on. All three methods are implemented with a frequency of 5 Hz. And after comparing these different methods, we analyzed the impact of integrating Hyperledger smart contracts for the role allocation also, and as a distributed and cooperative decision-making process. ROS2 Go implementation is naturally faster than the interpreted ROS1 Python node. However, both implementations are fast enough for meeting the frequency defined for the role allocation. The addition of Hyperledger Fabric interface to the baseline Go implementation increments its latency. However, it still remains fast enough to meet the 5 Hz requirement for the system. And as the last scenario that we have recently worked on, a Hyperledger Fabric network bridges robots with the remote teleoperation application. The Fabric network is able to transport data with low latencies in the range of hundreds of milliseconds. Real-time data stream can be confirmed through hashes in the blockchain. The Fabric network allows for control access management and auditability of the teleoperation. So we proposed Fabric as bridging the interfacing ROS2 system. So using the Fabric as a bridge with ROS2 system through an event-based design and parameterizable data transport setting. And also we introduced the design, implementation, and evaluation of a proof of concept for near real-time robot teleoperation through Fabric from single to multi-robot systems. Comparing to previous experiments and scenarios, these experiments is toward near real-time remote teleoperation and control. It's more lightweight, computationally efficient Fabric ROS2 bridge. And we ported from Go to Node.js. So despite Go, which required the predefined ROS2 message, Node.js doesn't require this. And it's, in general, it's a more generalizable and performance Fabric ROS2 interface. So this is a system architecture overview and illustration of the ROS2 and Fabric blockchain interfaces. The Fabric network effectively acts as a data transport layer between individual ROS2 subsystems. A Fabric network is optimized for cross-organizational data exchange and secure, tamper-proof data storage and sharing. Event-driven architecture is the key feature of this paper. Research where ROS2 Fabric applications execute callbacks from both the ROS and the Fabric networks they are interfacing. ROS2 events occur whenever, for example, new message arrives or new messages are published to a given topic. This approach significantly reduces data transport latency at high network capacity. And as a hardware setup, we utilized, for this experiment, we utilized the DJI Teledrone and also the mockup system in the area of 8 to 9 to 5 meters for the localization. So here you can see the software architecture. The system was implemented based on the ROS2 Galactic framework on Ubuntu 20. And robot control and localization were running in host 1. Data from OptiTrack mockup system camera is received with the VRPN client ROS node and used for accurate position and attitude of the robot. And the teleoperation application and the basic motion controller were running in host 2. 2 Fabric applications are then deployed in each host to interface with the ROS2 system. And the latency is also calculated since odometry message is generated in one host until the matching velocity control message for controlling the to go to the predefined path arise from another host, including both the physical network and the fabric network latencies, which you can see is more or less around 0.5 milliseconds. And as a conclusion, we leveraged blockchain technology for multi-robot systems in various industrial applications for purposes of identity management, data sharing, security, monitoring, and multi-robot inventory management and consensus. We showed that using Hyperledger Fabric and robotics systems provides a significant amount of built-in security while having a minimal impact on the utilization of the computational resources. And in overall, the integration of Hyperledger Fabric and ROS2 empowers distributed robotic systems with enhanced capabilities and trustworthiness. And of course, we are a team, and I haven't worked alone, and I couldn't do this without the help of my friends and colleagues. And so thank you for your patience and listening. Thank you so much.
Thanks, Salma. And participants can ask questions directly or they can write in the chat. So we have some questions, Salma, in the chat. So first question is about LiDAR and machine vision can be used to complement each other. Is there any focus with ROS2 R&D to merge the two technologies?
Basically, I haven't worked on LiDARs and machine vision, so maybe I cannot help you with that, but I haven't worked with that, so I cannot say exactly, but I can search and I can reply you later. I can ask, because some of our colleagues are specifically working on LiDARs, and we have other colleagues working on machine learning and visions side, so I can ask them and later answer your question.
Thanks, Salma. And
is there mesh technology used for ROS2 solutions? Yeah. No, we haven't used mesh technology. No, we haven't used for our ROS2 solutions.
Salma, you mentioned one thing like identity management. So how you are using this with respect to blockchain?
So the basic idea is that all the robots that are in the system are defined before, so we know the identity of them. So they are kind of members of the network, so that other robots do not come and be like Byzantine the system. Currently, we are working on the scenario now that we have a Byzantine robot, so we are more focusing on the identity management part, and we are using the ABAC smart contract of the Fabric, which is going to be published later, so you can see the result. But basically, the idea until now was that, so all the identities were defined in the system.
And one more question on ultra wideband. So what are the use cases, other use cases, like what kind of devices we can connect with this? And if you can tell us the frequency as well, that's really helpful.
Basically, my colleague is working on ultra wideband, but the main usage that I have used for all these experiments is only for the localization, and the thing is mostly we use mock-up systems, but as ultra wideband are more affordable and easy to use, I have used them in some of my experiments to see the results also. But for the other systems, I think they can be portable, they can be connected to the different robots also. But if you have any questions about ultra wideband, you can connect my colleague Paula Torrico Moron. So she is the specialized person for the ultra wideband part.
Thanks. And about the standards, so do we have standards on this right now, or which is the standard body for this particularly?
What I didn't get you.
For ROS2?
Yes.
So is there any standard body who made all these standards, or is it what is it like? Is it open source or?
Yeah, it is open source. So currently we are working with ROS2 Galactic. So it's easily used and open source, and it can be used for different robots, and it's easy to use. Also, we have all the packages and things in our GitHub repository. If you want, for example, the smart contracts and applications that we have used for our scenarios are, I can send you later in the GitHub, so it can be used and compatible to other robots, and you can easily use them.
Yeah, that will be great if you can share the GitHub profile. Yeah.
Yeah, of course. I can add the GitHub repository in this slide, and then later when I send the slides, when you're sharing that, you can go and check.
Yeah, thanks, Salma. David, could you check any questions from YouTube?
I've got a few comments to say. So thanks, Salma, for accepting the invitation and for a great presentation. You've done quite a good bit of work here, and it seems that you haven't really stopped at trying to integrate the fabric with ROS2. So you've actually done some analytics work on kind of how Hyperledger and Fabric would actually work in these environments. Yeah. And I particularly like the way that you've used smart contracts, it seems, to kind of support the event-driven or enable the event-driven kind of nature of the work. So you're I think triggering these smart contracts based on the events that happen on the ROS2 side, right? So that's probably would save lots of resources in smart contracts just being triggered when they're needed, rather than constantly being kind of monitoring the system, right? So the part with the smart contracts, which is kind of the most interesting part for us in this group, kind of trying to see how people are using Fabric and chain codes and so on. So one of them particularly was interesting to me, which was the decision-making contract based on the battery level, I think.
Yeah.
If you can go back to the slide, because so some of your smart contracts are essentially about writing kind of data on the ledger, right?
Yes.
But this particular one was about actually kind of making a decision. So one thing that I'm a bit confused about is that so this is a decision making that's supposed to be taken in a distributed manner, right? So there should be some essentially entities that don't trust each other, right? And now they want to make this decision together without trusting each other. So can you just elaborate on that scenario? Like, why wouldn't they trust each other, and what are these parties?
Why wouldn't they trust each other?
Yeah.
So the thing is, for example, here, Dashko and Telo are not connected to each other. They are not aware of each other's condition. So smart contracts only checks the topics that is getting from the Telo, which is the battery. And whenever it gets the topic that the battery is lower than a specific, it just publish the topic. So the ROS, so on the other side, in the Dashko, which we have the smart contract also, when it gets that topic, it's go to that task, goes to that position. So basically they do not, both of them are from parts of the network, but they are not aware of each other. They just get like publish and subscribe. They just subscribe to the topics and publish, and with these they just communicate. I don't know if I get your question right or not.
No. So yeah, maybe I misunderstood the point here. So so what you're saying is that there is a server and kind of node relationship here. So the idea here is not achieving trust using the smart contract. It's more about just data transparency.
Yeah, trust side is for trusting the robot. because, you know, for example, our scenario was using them in the warehouse environment. If another robot try to make faults in the system, or try to, for example, get the drone for landing, or do some faults in the system, that robot cannot see any topic, because those topics are going through the blockchain, so it's not available outside that. So only these two can communicate and can see the topics. Another thing which we are currently using also is that there is another thing, like beside ROS2, SROS has been developed recently, which is secure ROS2. With that case, if we implemented that also, each robot would have some keys, and with those keys, nothing out of those robots would see those topics. So basically, it's like that. But we are using it currently. We are trying to use the SROS2 with the ABAC smart contract this time for this identity and trust things. But basically, yeah.
Okay, so now, so if you want to talk about the kind of the setup of Fabric that you have, right? So do you have multiple organizations? Do you have like, so because these smart contracts are essentially, probably you don't need a very complicated endorsement policy for them, right? So do everyone in the network have to endorse these smart contracts, or?
Only the robots which are going to involve in this. So nothing else. This smart contract is only by these robots. So no one else. I mean, you can, if you're in a system, you can see the topics, but you don't need to endorse the smart contract.
Right. So I can see, like, in more sophisticated scenarios, like let's say in a factory of future scenario where you might have let's say machines from different let's say sections of the factory trying to work together. So maybe in those cases you might need kind of smart contracts that are essentially kind of bringing more of that, you know, collaborative decision making kind of side of things to the smart contract. Because then you have the problem of trust, right? So because now you have external sources of trust, and how do you trust people coming in and out? I know that you're planning to use smart contracts for identity management as well, but what I'm talking about here is more from the view of more complicated decisions that have to be taken, and more people have to give an input. So here, your input comes directly from the drone, and the drone makes the decision based on its battery level, right? Okay, yeah. So there's quite a bit of things to be done here in more complicated scenarios.
Yeah, of course. I mean, we are just starting this. I mean, I recently just started working on Fabric from a PhD. I mean, it's been 1.5 years, so I'm just trying to integrate. I was not specialized in blockchain.
And one last question. So if you go to the latency figures that you had, well, actually, like both latency and CPU utilization.
Yeah.
So what is the transaction throughput here? What numbers are you looking at?
The thing is, we had another analysis also, but I didn't put because the slides were too much. For checking the throughputs to see that if changing, having different throughputs would affect this or not, we had some tests with different batch timeouts and maximum message. But beside that, we got the frequency of I mean, with the frequency of around 50 hertz was the thing that we got the optimal one, but we had some stress tests to check the different frequencies and different utilization, but I didn't put it here. So with that optimal frequency that we got the minimum resources utilization.
Yeah, but sometimes that's really out of your control, right? Because the number of transactions that come through your fabric will depend on the number of drones you have. So I assume these are all scenarios with one drone and one dash, right?
Yeah, only for our case. I mean,
okay.
It's not.
Yeah.
Yeah.
Yeah. So I mean, obviously, for this case, this is a good analysis, but I wonder if this would still apply if you have, let's say, 100 machines that are quite latency sensitive. So you want to process their transactions very, very quickly.
Sure.
So yeah, what I'm saying is that this might not be very generalizable because like I did lots of kind of these kind of analysis on whether if my fabric network is going to kind of be able to meet the latency requirement that I have in my use cases, right? Which is telecom use cases, and they're very latency sensitive. And once you reach kind of a couple of hundred transactions per second, things start to kind of change quite rapidly with the latency and CPU usage and so on.
Yeah. Also, when after recently, because with our new scenario that we are using, the one problem is that as it is accumulating the data after, if we leave the data to be transferred as it is, sometimes the latency increases, even though it needs, for example, after 3 minutes or 4 minutes after accumulating the message, it starts to go up.
Yeah. And there's also, so one thing is actually like just writing things on the blocks. And the other thing is that if you have like a kind of a more sophisticated smart contracts that are making a decision based on a particular algorithm, then if you have to wait for all the nodes to endorse your smart contracts outcome, then you end up sometimes waiting for quite a while for everyone to endorse the smart contract and so on. So yeah, very, like lots of space for you to work on if you want to continue working with Hyperledger. So
yeah, of course, there are lots of parameters that we have to take into account, and if we want to generalize it, of course, we have to use more than 2 robots. We have to take into account lots of things. Of course, you're right.
Okay, perfect. Thank you very much.
Thank you.
Anyone else? Any questions?
I have a question. So, very wonderful presentation. Thank you so much for your time. My question is, are you able to bring the electromagnetic computation into Fabric?
For now, I have to search for that because I don't know if I can. I don't know. I have to.
Like the frequencies. Are you able to bring like the RF and all of these things into Fabric?
Yeah, that's why I'm saying. I mean, like checking them or.
Well, anything. I mean, it's just, I mean, you're on the cutting edge.
Yeah.
So I'm just wondering if you were able to bring electromagnetic computation into Fabric.
Actually, we haven't tried. No, so I cannot give you an answer. We haven't tried. So maybe if we try, I can give you the.
Okay. All right.
Yeah.
All right. Thank you.
You're welcome.
Anyone else? Any questions? If not, so thank you, Salma, for accepting our invitation and this very good presentation. And thank you, everyone, for joining today. And
thank you for listening.
Thank you so much.
Thank you.
Thanks, everyone.
Thanks, everyone.
Bye-bye.
Bye.